Alright, so today we're going to be talking about inverse functions and their derivatives. And then we're going to be focusing on trigonometric inverse functions and trying to derive the derivatives of each of those trig functions. So let's just talk about what an inverse function is first. So basically we know that if we're given a function y is equal to f of x, we define an inverse function f inverse where it will take in y and return x. And so if we have this function f inverse that takes in each y and returns back x, then we can call f inverse the inverse of f, right? And so that is our inverse function. And if we were to graph out f of x and f inverse of x, we would see that in f of x, we would get points a comma f of a, and then if we were to graph out f inverse of x, our points would be f of a comma a. And this sort of, if you kind of know something of geometry and the relationship when you get a comma f of a, and then on the inverse function, that point being f of a comma a, this is the same thing as reflecting across y is equal to x line. So essentially, geometrically, when we plot out the normal function and the inverse function, the relationship between the plots is that the inverse is simply the normal function reflected across the y is equal to x line. And so let me just show you an example of that. So let's draw this y is equal to x line over here. So this is y is equal to x. And then let's consider the function x squared, okay? So y is equal to x squared, only defined on when x is greater than 0. So x is greater than or equal to 0. So we have this, and then let's say we have point 1 comma 1, and then 2. So this is 2, and then 3, or 2, 3, 4, right? And then we get this like quadratic formula. So this is f of x, right? Now this is f of x. And then if we were to get its inverse, we know that it's the square root of x. So similarly, we would have 4 comma 2 over here, and then we would have 1 comma, we would have, oh actually, okay, this is not to scale. So in y is equal to x, like all of this sort of intersects right here. So this, let me just draw, and then you would have something like this. So the idea is we have this y is equal to x line, and everything, if we were to plot the inverse function, so this is f inverse of x, right? If we were to plot the inverse function from the regular function or vice versa, we would just have to reflect across the y is equal to x line, and we would get the other function. So 2 comma 4 over here, and then we have 4 comma 2. And so we kind of see this relationship that we sort of drew out in that case, right? And this has pretty important implications for the derivative. And because of the fact that if we want to get f of a on the inverse function's graph, the corresponding y value is simply just a. We can use that fact and come up with this relationship where if we were to find the derivative of the inverse function with respect to x at f of a, that's the same thing as finding the derivative of f with respect to x at point A. So essentially, this relationship is very important because at times it can be very hard to find the inverse function or the regular function, but we do know one of the functions, right? And so we can utilize the derivative of the function that we know at various points and come up with the derivative of the inverse function through this relationship. And I guess like I can provide some intuition for how this relationship comes to be. we can kind of think of the regular function, the derivative of that at a certain point a, right? So let's say a is equal to 2, right? The derivative of f with respect to x at x is equal to 2, that is just the rate of change of x, or it's the slope of the line at x equals 2, right? So we have this sort of slope here that we're finding. So it's the slope of the line at x equals 2. And now we're reflecting that across the x-axis, or across the y is equal to x line, and that will, when we reflect that point, we get 4 comma 2, right? And so on the inverse function, when we want to find the derivative of the inverse function at point 4, we know that at that point, because it's on the inverse function, we just switched up the x and y's, right? So in our regular function, we had points x comma y's. So in f of x, we had points x comma y's, and our sort of slope looks like change in, so delta y over delta x, right? And then in the inverse function, where you have f inverse of x, right, the points just become y comma x's. And so now we have delta x over delta y. And if we perfectly match up the corresponding y values and the x values, such that we know which points are reflected, we know we have this reciprocal relationship, because essentially finding the derivative is just like finding the slope. So if we had delta y over delta x on the regular function, at point y comma x in the inverse function, we simply, the derivative is simply the reciprocal, and that's exactly what this relationship is mapping out over here. And this all comes because of this important geometry that we have through the inverse function, where we're reflecting across the y equals x line, and at inverse, and in an inverse function, each x comma y pair just becomes y comma x. So if we want to find the derivative of the inverse function at point y, we simply can find that by finding the reciprocal of the derivative of the regular function at point x. And so this relationship over here that's been mapped out is very important. All right, so we have that. And so this kind of brings us to a general statement, or a theorem. And the theorem is pretty simple. It just states that if we have a function f that is differentiable at every point on I, and is not 0 on those points, then f has an inverse, f inverse, which is also differentiable at every point f of I, where this f of I just means I'm taking every point on interval I and then applying that function f, because our y's become our x's in the inverse function. And so this theorem just states that if we have some function that's differentiable, right, and it's not 0, because if it was 0, then the derivative of the inverse is undefined, right, because we're doing the reciprocal. If we have that, then we have an inverse function and it has a corresponding derivative, right? And so this kind of guides us on how to sort of find the inverse of how to find the derivative of certain inverse functions. And we will go through specific examples of deriving them by working through finding the derivative of 3 major trigonometric inverses. And that will kind of get us used to how to find derivatives of inverse. So let's start off with the function sine inverse of x is equal to y. And start off by finding the derivative of y with respect to x in this case. And so whenever we're dealing with inverses, it's really important to kind of understand how this function looks like, because not only is that going to guide us about the range and domain of the specific functions, it's also going to guide us about where our derivatives exist or not. So we know that sine x at least looks like this, right? We have some sinusoidal thing right here. Okay, that was bad. Right? This is 0, this is pi, and this is negative pi over 2, right? So that is sine x, right? This is sine x, and then our inverse is basically going to be something like this, where I would have this, and then this, and then it just repeats like that, but we want to make sure that our inverse is also a function, so it passes this like vertical line test. So we're going to make sure that our inverse is only going to be defined from negative pi over 2 to pi over 2. And then that means our range is going to be from 1 to negative 1. So in this sort of vicinity, this box right here, that's where inverse is defined. So in here is where sine inverse is defined. It kind of looks like the cubic function, but it really is not, right? So that's the domain we're concerned with. So over here, our domain that we care about is from negative pi over 2 to pi over 2, and our range is from 1 to 1. And similarly, on the regular function, we only care about the domain of negative. We only care about the domain from negative pi over 2 to pi over 2, right? And so, oh wait, I think, yeah, this is, I drew this wrong. This should be pi over 2 negative, and then this should be positive pi over 2, and then this is negative 1, and then this is positive 1 over it. Let me get the eraser. Right, so yeah, so this is negative 1, this is 1. So in the inverse function, our domain is from negative 1 to 1, and our range is from negative pi over 2 to pi over 2. So it's like this box right here. And our derivative won't be defined at these two corner points because of the fact that it's going to become a vertical tangent. So our domain is only really defined in the open interval of like x between. So our derivative is only going to be defined in this range, right? So now that we kind of know what these functions look like, let's try to tackle how we're going to find the derivative. So we can write sine inverse of x as sine y is equal to x, and that comes just from the inverse properties. And from implicit differentiation, we can kind of take d over dx of sine y is equal to d over dx of x. And then we get cosine y times dy over dx is equal to 1. And then simplifying, we get 1 over cosine y is equal to dy over dx. And so unlike in normal implicit differentiation, if we were just given this, we could stop, right? Because we have the terms sort of separated out where dy over dx is separate, but we were given sine inverse of x is equal to y, so we need everything in terms of x. And so cosine y, because of the like Pythagorean identities where sine square of x plus cosine square x is equal to 1, we can rewrite this as 1 divided by square root of 1 minus sine square y, right? and that is equal to dy over dx. And then we know that sine squared y is just equal to x squared because of that expression. So this is just 1 over 1 minus x squared and the square root of that. And so essentially our inverse function, so the derivative of this function is simply, so dy over dx of sine inverse of x is simply 1 over 1 minus x squared. And then this is defined between x is less than 1 and greater than -1. And we can kind of tell from over here where the denominator would be 0 if we had equalities, and the original like sine inverse function also is just defined in that range. So that is the inverse of sine and the derivative. Now let's work towards tangent. So let's find the derivative of y is equal to tangent inverse of x. And the process is pretty similar. Let's first look at how tangent inverse looks graphically, right? So we know that we have something like this where this tends towards where our horizontal asymptotes are negative pi over 2 and pi over 2, and our domain is simply all real numbers over here, and our range is between negative pi over 2 and pi over 2, right? And so using that information, let's proceed similarly to how we did in the last one. Let's proceed similarly to how we did before, and let's find the inverse of tan. We find the derivative of the inverse of tan, so we can rewrite this as tangent of y is equal to x, and then doing implicit differentiation, we get secant squared y dy over dx is equal to 1, and then we have y dy over dx is simply equal to 1 over secant squared y, and we can again use the Pythagorean identity of 1 plus tan squared x is equal to secant squared x, and then we can rewrite this as 1 plus tan squared x. And then kind of eerily similar to before, we can use this equality and rewrite this as 1, and this should be y over here. We can rewrite this as 1 over 1 plus x squared. And so that is equal to d over dx of tan inverse of x. Oh my. And we know that this is defined for x in all reals because of the fact that our tan inverse is defined between that, or we could also kind of take the case of looking at where tan x is defined, and we know that the domain of tan x that maps to the inverse is tan x between negative pi over 2 and pi over 2, and in that sort of domain the range will be negative infinity to infinity. And so so essentially what I'm saying is this is tangent x, so I'm graphing out over here tangent x. We have pi over 2, negative pi over 2, and it looks something like this, right? So in tangent x, our domain the domain that maps to the inverse is negative pi over 2 to pi over 2, right? And that range is negative infinity to infinity, right? And so this new range becomes the new domain of the inverse function, and then we can be assured that our range of the inverse function is also range of the inverse function is negative pi over 2 to pi over 2. So that's a really easy way to find the domain and range of inverse functions. And then we can kind of test for sort of critical points or corner points where the function derivative won't be defined. But in this case, the derivative is defined over all x. And then we've covered tangent, we've covered sine. Now let's go with secant, right? So secant's actually the most complicated out of all of them. So we have y is equal to secant inverse of x, and we know, let's first graph out what the inverse function kind of looks like. So secant inverse, it's kind of interesting where our domain is it's kind of split. And so this is pi over 2, and then we have pi, and then right here. So we have this horizontal asymptote at pi over 2, and our domain is basically x is greater than or equal to 1, or x is less than or equal to negative 1, and our range is from 0 to pi over 2, and then pi over 2 to pi. So our domain's that, and then our range is simply from 0 to pi over 2, where 0 is included, and then union pi over 2 to pi. So the only point in our range that's not being defined is at pi over 2. And that comes from the fact that if we look at the secant graph itself, it's like a bunch of parabolas with like their vertex at 1, and then it goes off into infinity, right? And so essentially, if we look at that as the domain, that means our range will be, or the domain of the new function will be x is greater than or equal to 1, and then less than or equal to negative 1 as well. Right, so knowing that, let's go and approach how to find the inverse. So as we did before, we can write secant y is equal to x, right? And then the derivative, we use implicit differentiation like before, and then we get secant y tangent y times dy over dx is equal to 1. Solve for dy over dx, 1 over secant y times tangent y. We already know secant y is equal to x, and then we already know that secant y is equal to x, and then tangent y will be something else. So this will be equal to 1 over x times tangent of y, right? And then through the Pythagorean identities, we know that square root of secant squared x minus 1 is equal to tangent x. And this is like plus or minus. But here's where the tricky part comes into play. In this case, this plus or minus is very important because over here, the x value that we're gonna be taking into account, where x right here is like the range, the range is going to be from from pi over 2 to pi, or 0 to pi over 2. And if we know about the tangent function in that range, from 0 to pi over 2, tangent's positive, but from pi over 2 to pi, tangent's negative. So from 0 to pi over 2, so in this first range, we're going to get back square root of secant squared x minus 1. But in this other range, we're going to get back square root of secant squared x minus 1. And then it's going to be a negative over here, right? And that is what is y. That's what y is equal to. Which makes sense. Which makes sense, right? And so, how do we like reason about that when we're going to cover the derivative, where each case needs to be each case kind of needs to be covered. So essentially when the range is between 0 to pi over 2, we also know that the domain is this. And similarly, we know that the domain is less than or equal to -1 when we have this part of the range. And we can kind of leverage the fact that in the first sort of section, x is only positive and we want a positive, and here x is only negative and we want a negative. So if you kind of think of absolute values, that can help us sort of solve for this equation. So let me first write this down. So right now we have something like 1 over x times square root of x squared minus 1, and that's because tangent y is simply equal to square root of secant squared y minus 1, and then this is plus or minus. And depending on what y value was there, and y value in this case corresponds to this range, depending on what y value was there, the positivity and the negativity is affected. But we also kind of ascertained that when x is positive, so now we're looking at the x's, when x is positive, our y, or this output of the square root is also positive, and when x is negative, the output of the square root is also negative. So one thing we could do is we notice that essentially if x is negative, we're gonna have this is a negative term, and we want this to return a negative term, but in the end we want a positive value out of it. Similarly, when x is positive, this is positive, this is positive, we want a positive value out of it. So no matter what the case is, we want a positive value. And we know the square root function will always give us a positive value out, but not this function. There's nothing that determines positivity for that. And so we can essentially just transform it into absolute value of x times x squared minus 1, and now we're guaranteed to get the right relationship. And so this was like kind of a tricky case where we had to think through how the functions look like, but it was a needed case to determine the inverse of the secant function, or the derivative of the inverse of the secant function. So in the end, we got d over d, that is equal to d over dx of secant inverse of x. All right, so now there's three more inverse functions, but we kind of know that sine, cosine kind of similar, tangent, cotangent, cosecant, secant kind of similar, right? And the good part is we don't have to derive their derivatives, because we know that cosecant or cosine inverse of x is simply pi over 2 minus sine inverse of x, and then similarly cotangent inverse of x is equal to pi over 2. And then cosecant inverse of x is equal to pi over 2 minus secant inverse of x. So together, these are called the cofunction identities. So because of this relationship, we know that the derivative, so d over dx of cosine inverse of x, is simply equal to negative d over dx of sine inverse of x, right? Because of this identity. And we've already solved for the derivative of sine inverse. We've solved for the derivative of tan inverse and secant inverse. So we can use the cofunction identity and the properties of derivatives to then just find out the derivative of cosine inverse, cotangent inverse, cosecant inverse. But similar, you can use what we did to prove the derivatives of sine inverse, tangent inverse, and secant inverse to come up with the derivatives of cosine inverse and etc. But it will just be more annoying, I would say. So yeah, that is the inverse of the derivatives of the inverse trig functions. They were certainly not very easy to derive, but hopefully that gives an idea of how to derive the derivative of inverse functions.